Okay, thanks a lot, Sripana, for hosting me. So I don't know, probably you are already overwhelmed because you are like learning things from since morning. I don't know what time you started, but yeah, of course. So I will not tell you something today at least that is in practice in industry. That I have kept it for tomorrow, like what we do in industry. Today I'll tell you what we used to do in the industry probably a year back or so, means couple of years back. So to start with, like I will covering like neural text generation, which essentially came to today's AI assistance model. Like all of them boils down there itself. Now, okay, let me get used with this. Okay, yeah. So this is the thing I'm going to cover. I will give you a brief introduction. Then couple of models. I do not know whether you are already familiar or you have already learned some of these model in this course, like ExcelNet, ProfitNet, GPT-2 and 3, and then T5, BART, autoregressive transformer. But just for my understanding, I'm assuming that all of you are well familiar with the transformer. Is that correct? Okay. And then I'll give some outlook and summary. So this is what probably like if you would have asked like, okay, 2 years back, what kind of technologies are used, probably some of these are true. Now today in industry, none of these are truly relevant. Yeah. Oh, sorry. Okay, you can keep it, yeah. Thank you. Okay, so natural language processing, like as you know, this is the holy grail of AI. Like if people thinks that if you can solve this problem, then probably you are doing like real AI. Now there is debate, of course, because we are already at the end of the day. I'll tell you some stories also so that you get motivated. So people thinks like earlier playing chess is AI. Then you solved playing chess. Like then they said, no, that's not AI because there is nothing. The number of moves is finite. So then they said, okay, can you understand a natural language? Can you do something in natural language? Then they thought like, okay, that probably AI. And then people solved that problem as well. Currently, like natural language is also mostly solved because of GPT and stuff. Then people are saying like, then what is AI? Now they're saying that, okay, not only understanding natural language, acting on that is AI. Like, and GPT kind of model is already doing that. If you say like, okay, call my friend, through phone it can do actually. I don't know, probably you haven't seen those kind of thing. And even you are saying GPT like draw a picture. So it's doing like GPT Vision, GPT V, all those things. Now, when NLP was started, its goal was to pass the Turing test. Now, if you know Turing test, probably some of you know, that you won't be able to discriminate when you are doing a conversation with someone outside the curtain, that whether it's a machine or a human. If you cannot distinguish and actually a machine is doing the conversation, then actually you are passing the Turing test. Now that's the goal, and probably ChatGPT is doing that. Controversial, but it's kindly somehow there. Now, these days, Turing test is not the test which people follow, but yeah, earlier, like if you win Turing test, you used to get a Loebner Prize, whose prize money is like, I don't know exactly, but $250,000 or something. And many people have won that Loebner Prize. But nowadays, there is a new test has come, which is called Octopus test. Now, of course, I'm not going into that detail of Octopus test. It is very recent. I think it's from Emily Bender. So now it has two components, natural language understanding and natural language generation. So these together makes NLP. Now, one thing before I move forward, like you can ask me, interrupt me anytime, any question you have. Don't think any question is a bad question, like all questions are good questions. Now, so when we started natural language generation, like in the history, now it's a process of producing meaningful phrases and sentences. And I don't know how many of you have seen this ELIZA, like which was 1964 kind of a pattern-based system, which used to do dialogue-based conversation. And it was in MIT. So, and that time mostly it was template-based. Like you can imagine, like you have to write rules and that requires like content planning, what kind of content you are going to put and where should be they should be placed. Then word choice, multiple word you can use, and which of them where should you use, all those like disambiguation, aggregation, combining phrases, sentences together, proper syntactic writing, morphology, or all those things used to be done. But that's history. Nobody does that. Even if somebody does that, it will be considered okay, primitive things people are doing. Then it came like dynamic creation of content. One of the popular example is Markov model. Like you can emit tokens every time. But Markov model is also very old. Markov by process is 1913, I guess. So that's fairly old. But of course, like neural network based thing is also you can consider as like a recent dynamic document creation. Now here are some examples like which are like very useful. One is machine translation, and the things in bracket is indicating some popular data set which you can use. WMT is a very well-known data set for machine translation. Then abstractive and answer-aware question answering system. ELI 5, I think ELI stands for explain me like I am 5 years old. Summarization, like that's another important thing. Dialogue response, conversational AI. So I'm not going into this detail. You will get the slide. You can go through this data set, and if required, you can find the detail. Now, in the history, like if you see earlier in here, like this linguistics versus data. So earlier NLP was mostly like linguistics driven. Like you write rules, you write morphology, syntax, semantics, semiotics, all those terms used to be there. Now it has changed its dimension. It's all data. And then that famous comment came like data is the new oil. And people believe, I think like Mukesh Ambani said this, but I don't think he is. It was by some mathematician, Hambi or somebody. Now, here in the history, if you see like 1950 to 1980, it was mostly dominated by rule-based system. Linguists used to rule the world. And that time, ELIZA came like 1964 from MIT. Then at that time, though this was popular, but many machine learning algorithm evolved, like say Markov process, ID3, all those algorithm came this time, and they became popular during the time of 1990 to 2000, 2000. And linguistic insight with some data came into the picture. Like, well, you use some amount of machine learning. And this time, like Lake, SIAC, all those parsing language also came. And in 2000 to 2010, large scale model like support vector machine, and there was SGBoost, all those kind of things. And like people started with playing big data. And then there was that infamous statement by, what is his name? I forgot his name, Fred Jelinek, yeah. So he said like, every time I fire a linguist, my system accuracy goes up by 5%, which was very infamous statement because he said like, okay, probably we don't need linguists, we need the data. I think it was 1984 or 88, sometimes he made this comment. And by the way, he's a ACL Lifetime Achievement winner. It's not somebody random said that. Now it came about deep learning, 2010. So where the models were like all like supervised neural models, like RNN, LSTM, all kind of CNN, but that requires a lot of data. And from 2020s, it's all multilingual zero-shot learning. Like you don't need to do anything. Use only unlabeled data, build the model, and then prompt. So it will give you the whatever the desired task you want to do. Now, when this evolved, you can see the amount of model that is coming into the literature. And the central piece is, of course, here, BERT. Now, BERT is not the first model, but maybe the very first popular model which came to like everyone's notice. So, and this model, before BERT, like there are two models. One I will say like ULM-FIT, and then there was ELMO. These together actually contributed the development of BERT. And like BERT was developed in Google by Jacob Devlin, who is the first author and the last author of the paper, I think Kristina Tortonova. Unfortunately or fortunately, both they were in Microsoft, like they were in my team as well. So that was like a great thing. Now, so here I just want to see, like, this is a 2020 picture, and you can see the number of models here. Like, and after that, like, there are a lot of models. So from Microsoft, the model like Turing, NLR, ULR, NLG. NLR stand for Natural Language Representation, ULR for Universal Language Representation, NLG for Natural Language Generation. So different version came. Then UniLM, G-code, ProfitNet. I will talk about little about ProfitNet because that's like slightly more advanced model. And then in the generation part, like after UniLM, BART, MBART, XNLG, T5, all those model came. Now, and on the other side, that decoder-only model, you can see like after GPT, GPT-2, like all these recent models which are in practice, like starting from Llama to Gemini, they are using. And you can see the amount of data and the parameter this model are using. Like GPT-2 has, I forgot it, how much it has, but see GPT-3 has 45 billion words and like 175 billion parameter. That's a huge space. Now, so together this is where we are. Now it's not only important that your parameter space will make your model stronger. It is not, because if you see here, say GPT-3, it has 175 billion parameter, and whereas say Llama, it has only 70 billion parameter. Does that essentially indicate that GPT-3 is a better model? Definitely not, because GPT-3 is trained on only 45 billion words. So that means it's trained for lesser amount of time, whereas Llama was trained for 1.6 trillion words. So it has more knowledge. So, and if you see in literature also, you'll find that Llama is from 2023, which is fairly much more advanced model than GPT, which is from 2020, GPT-3 especially. Now, these models primarily have 4 different areas where they differ. Like one is learning objective, what objective function they are trying to achieve, the data, how much data you are pumping into the model, and the vocabulary. Vocabulary means the amount of token that you are using, and training regime, like what kind of training, how long you are doing, all those like training hyperparameters. Now, so that's the basic introduction where we are. And some of the model, I think like the basic model you probably already aware of, BART and all those. Now one model that came quite some time back is called ExcelNet. So if you look at the timeline, that word2vec is like, I think 2014, when that Thomas Mikolov said like, okay, words should be represented by a vector, and that made revolution. And then after that, like people normally know this work, like Transformer, which is like by Vaswani, like the one which is the like attention is all you need. And before that, there are one work which is normally people do not connect with this, but I think it's good to read this one, because this is the connection from word2vec to this work. Like this is by Bahadunu and Kong-Yung Cho. Like they together for a machine translation problem, they said like, okay, we need attention to all the words. And that's called soft attention. So from that soft attention, they came to this self-attention. Now these two together, if you read, that will be a nice reading, like, okay. This work also not only motivated by on its own. Before that, like if you go back, like there is something called IBM models. Now IBM models has some metrics. So those metrics are captured in this soft alignment. So this is like, if you directly read like word2vec to Transformer, I'll say like, okay, don't miss this paper, like which is soft alignment by Bahadunu. And then like you have other models which came in parallel with Transformer, like Elmo and ULM-FIT, of which like ULM-FIT is the one which, if you read that this is the first one which said that you can, instead of doing supervised learning, you do like pre-training and fine-tuning. And this was this guy, Sebastian Ruder. he said that it's a matter of time that when everyone's computer will be populated by a pre-trained and fine-tuned model. And then rest of it is history. Like from once this transformer came into picture, then GPT, BART, and all the model until like GPT-3 until May 2020, it all emerged. Now this model has two properties. Either from the learning side, either they are autoregressive or they are autoencoder. Like, are you familiar with this term, autoregressive and autoencoder? Okay, so this is very easy, like there is nothing hard here. So these are the two primary approaches, like out of which one is used. So autoregressive is use observation from the past to predict the next value. So what language model does? It says like A, B, C, and then D. So, okay, I know A, then B, then C, and then D. So to predict D, I should go B, C, then B, then A. That's what it does. So it's auto-regressively. It's look back all the tokens one by one. And autoencoder says reconstruct the original data from the corrupted input, what BART does. Like you mask the input like randomly, 15% of it BART does, and then you say like, okay, predict this. Now, so for example, like here in this, if this is a sentence, New York is a city, in auto-regressive fashion, what you will do, so new will predict York, like here, then York will come here, you predict is, then is come here and you predict A, and then you keep on going like this. That's auto-regressive. Now you can decompose it. It's completely based on Markov chain. So this is your sentence. You want to maximize the probability of this, and you can decompose it. You can factorize it that whenever you are in a current token, that depends on all the previous token. And you can do it also reverse way. You can say like, okay, how to erase it? Yes. You can say this, like backward, forward propagation and backward propagation. Both of them holds true. Like that you can do. Now, in autoencoder, which was, means earlier this autoregressive was the model kind of thing, and BART made this one is most popular. So here you just mask two things, like 15% of the token they generally do. So you have masked new and York here. These two token you have masked, and you are trying to predict. So here you are formulating that, okay, I want to predict X prime given the X hat, which is the corrupted input. And that's what is the objective. Actually, it's not equal to, it's near equal to. So because it's not the, because of this masking, it doesn't decompose that probability of this. If you multiply that, you will get the probability of the entire thing. So it's a near equal to probability because you are masking things. Now both, this has like advantages and limitations. So the limitation, if we look, autoregressive, dependency between words on the left or words on the right, that's what you capture. So because here, you, to predict, say, if I say something, New York is a city, and then you just, say like, okay, I want to predict this word city, so it's only depends on the previous word. And you do not know what is coming next, so it doesn't. But here on the other, sorry. And it is like not able to model bidirectional context. So even if you have something on the right, you are not capturing that. So you are only taking the sequence that is in behind. Now, on the other side, autoencoder, it's predicting a mask token in the presence of other mask token. So that means, so when you are predicting new, predicting new, you have no information about what is this token. This token, you have no information. So you are only predicting with this three other token. And when you are predicting this, then also you have only this. You do not know about anything about this token. So this is the problem of the autoregressive one. Now, if that is fine, but it may happen they are not independent, like New and York. If they are not independent, then probably there is a chance like, okay, you will make a mistake like here, because New and York probably not independent, so you need to predict them jointly. Now to do that, so BART uses this one, like where it says like probability of New given is a city and probability of York given is a city. Now how BART will learn that it's New York? It can say New Angeles or Los York because it's trying to predict a two-word city name. And Los Angeles is also two-word city name and New York is also city name. So given is a city and I know blank blank is a city. So I know that means I have to predict a two-word city name and then the first word of the two-word city name is New and the second word of the two-word city name is Angeles. So New Angeles is fine for BART as well because it doesn't know that New and York are dependent. Now, so in ExcelNet, they said like, okay, autoregressive model, not just forward or backward, but with permutation on both sides. It's a tricky thing, I'll come to that. And not using LSTM, but self-attention. So if you use LSTM, that means the dependency between different layers are not captured, even if you use them bidirectional. Like if you may say, okay, I use your LSTM, I have forward and I have backward, I am concatenating them, so I am capturing both the context, so what's the problem? But the deeper layer, you do not have any connections, which is there in the transformer. Now in BART, we use this one, but in ExcelNet, we are saying, okay, predict your given New is a city, like New is a city, like because you are doing it auto-regressively. So you will predict first New, and once you predict New, then autoregressive one, so here like New York. Now if you have already predicted New, then this one you will be predicting like this one. So, so always you are predicting the next one with the dependency of the previous one. So that's how it happens. Now how you can do that? So in general, like autoregressive, like if you say New York is a city. Now you are trying to predict is A, then this is a natural factor 1, 2, 3, 4, 5. So this is the natural sequence, and you are predicting 3, okay, when 1 and 2 is available. Predicting 4 when this is your natural sequence. But and here it will always come in this order 1, 2, 3, 4, 5. Now who gave this factorization? Because we are assuming that, okay, this is the natural thing and that probability, like the current token depends on the previous token, that's giving us this one. But this guy said, like, okay, we don't need this natural factorization. We will use all possible factorization of a sentence. So here you can see, they said like, okay, instead of considering 1, 2, 3, 4, 5, my factorization order is 3, 2, 4, 1. That means in autoregressive model, so autoregressive I used to take 1, then 2, then 3, then 4. Now I am saying 3, 2, 4, 1. That means this is my new sequence where 3 is as good as 1. Like, so I will predict 3 first, then I will predict 2, and then I will predict 4, but all in autoregressive way. Like, so then what will happen when I'm predicting 3, I will say like, I do not know anything. I have to predict just the first token. So here you can see x3. x3 is nothing is known to me when I'm trying to predict. See, here nothing is known. But you can consider another factorization, like say 2, 4, 3, 1. And there, when you are predicting x3, you are actually using the information from 2 and 4. Whereas 2, 4, 2 is this one, 4 is this one. So you can see these are the two connections from there. Forget about this part. You don't need to worry about this memory thing that comes from transformer Excel. So these are different factorization order, and you can predict them in this order. Is that clear, like up to this point? Now, so then you have like, if it is a 4-word sentence, then you have like factorial 4 possible combination, but you cannot actually take all of them. So we have to do some trick there. So the trick is that you do them autoregressive way here, all before T, but on a particular sequence, sorry. See this G, where Z is basically saying that one of the possible permutation that is possible. Now you take some of the random permutations of the factorization and you try maximizing that. Now there is a tricky question. So everything happens in deep learning is in a single pass, because you cannot wait for one things to complete and then you will do that, okay, I will predict the next one. That's very difficult, because then it will take like ages to train the model. So to do that, like that means now when you are predicting x3, sorry. So when you are predicting x3, at the same time, probably you are predicting x4 as well. Sorry. So when you are predicting x3, that say you are predicting x1 as well. Assume that these two you are predicting at the same time, because you will be masking some of them and at the same time in one pass you have to do it. Otherwise it will take a lot of time. Now when you are predicting x3, you know that I know that x2 and x2 and x4. And you cannot use x3, because if you use x3, if you put a connection here, then what will happen, like it will not learn anything deep learning, it will just do a copy. Because in the transformer, that this one has a lot of information, it has the information of the content as well. So you cannot use this one. Now when you will be predicting one, that time you have to use, say suppose now at the same time you are predicting x1, so that means you will be using x2, x4 and x3. All these three connections will be there. Now x2, x4 and x3. Now the question is whether you know x3 or you don't know x3. If you know x3, that means here it will also use that information and it will not learn anything, it will just predict, like copy things, like it won't learn any parameter, it will just copy. But on the other side, I am saying that for this particular factorization, I need x3. So whether you will keep the information of x3 here or not. Now, to do that, they used a new like engineering kind of solution, and I think that's a very pretty neat solution. So they called it two-stream self-attention. So the model need to know the position of the token and need to separate position and content embedding. So because in one case, you just need the position. I want to emit that particular position, what should be the word, but I don't want to use the content, like which was true here. So when I will predict x3, I cannot use the content of x3, but when I will be predicting x1, which is the last, that time I will be using the content of x3. But when I will be predicting, when I will be predicting x3, I will just use the positional information. So that's why they did a solution, but before going into the solution, like I just want to refresh your transformer. So transformer has input word sequence like thinking machines, blah, blah, blah. And then you learn three vectors, query, key, and values. And you multiply query and key, dot product, and you get a scalar. And then you like do softmax and then weighted sum of like softmax into value. Then you get the particular representation Z. So G is basically the corresponding vector that you learn for a particular word. Now here there are three things. So now when you are doing these operations, what you are doing? So you are doing a dot product, Q and K1. So Q is basically your input and K1 is basically the all other sequences. Now, so when you are doing a dot product, you are getting a scalar value. So you are not essentially getting anything there. So it's not containing any content information. So the content information is here. So we have to like separate content and query, like position, because content and position, if we can't separate, then the problem of the ExcelNet we won't be able to solve. Now this is, because this multiplication is a scalar, so this is probably the content. And then we also need to separate the position. So position is here, because it's indicating that, okay, this is the current one. So probably we need to use two different streams, one containing the content stream, the other one containing the position stream, which is like the Q from the transformer. Now what they did, so they separated. You instead of one vector, they use two. One is the content one, the other one is the position one. Now, if you have that, then that problem is solved. Like say 3, 2, 4, 1, when you are predicting 1, so that time you will be using the content from x3, x4 and x2, but you will not use the content from this one. So this one you cannot use. You are only using the position. Same that the earlier problem we were seeing, that when we are predicting x3, we will predict from here. And that time we will not be using the content information. We will be only using the positional information. And this is a learnable vector, like you randomly initialize and then like you get that. So that's what they did. And that's easy to say, but it's hard to, hard to implement. But with this, what they achieved, so out of the 20 tasks, where they tried BERT, until that time BERT was the most popular model, they able to beat 18 of them. And that's the remarkable achievement, and that's really like great stuff. So that's one thing which is widely used in literature for natural language generation until GPT and all these recent model came. And then there are some sequel. This is easy. As soon as like if you get that in two stream self-attention, like basically you are dividing content and position. That's one thing you remember. Rest of the thing you forget, and you, whenever required, you read it like from the paper or book like that. There are ways. So takeaway is there are ways where you, instead of like in the general transformer, you have one vector, and what is there in that one vector? You have the content, you have the positional embedding, you have the residual network, you have the layer normalizer, so many things you add in that one single a hidden state. Now that is not always useful. For general transformer that useful, but sometimes like case like ExcelNet, when you need to separate them, probably you have to divide it into different things. You add everything, but you remove the position thing. So that means whenever it is required, you separate them. So there are techniques to do that. So that much is enough. Now, ProphetNet is a modification of that ExcelNet. So instead of two-stream self-attention, they tried like n-stream self-attention. That's what the only change is here. Rest of the things are like redundant because they achieved SOTA accuracy for this kind of task, which are like all like natural language generation task. But there is a caveat, like though it performed beat the SOTA accuracy. SOTA is state of the art, slightly lower accuracy compared to BERT and ProphetNet, the task that was tried in BART. This is bidirectional autoregressive transformer. So what it does, in general, like in normal case, x0 predicts the next token, x1, and then it goes like this. So from every state you like generate the next one. Now in ProphetNet, when it is bigram, so from one single you are actually generating two tokens, and then you are feeding one and you are generating. So you are doing future prediction. Like normally in transformer you do not do future prediction, just future is one token. But if you as a human, if you think like when you are writing something, you don't think about only the next token, probably you think little forward. Now here also they are saying like, okay, can you embed that knowledge in the transformer that instead of like planning for only one next token, plan for 2, 3 next token. And that's what they did through n-stream self-attention. So here is a kind of thing. You can see like, okay, beginning of sentence, they are like essentially predicting two things, like, okay, y1 and y2, position 1 and position 2 is generating that. Now once y1 is generated, then the next two position given these two beginning of sentence and y1, you are predicting y2 and y3 and so on. Like that's how it goes. So that's basically essentially saying do some future planning, not only like just emit the next token. This is the same thing. Earlier we had one positional embedding. Now here you can see I have this is the content and two positions for bigram. Like that's how it is generating. Straightforward. Like if you understand the ExcelNet, then this diagram has nothing. Earlier you did Only you divided the embedding into two parts. One is the content part, one is the query. Now you are, instead of two, you are dividing it to three because you want to do two future prediction. So that's how it's generating Y2 and Y3. And interesting thing, you can see that here, this is achieving like much better accuracy compared to many of the other state-of-the-art models. And here you can see for gigawords, it's beating almost all the model. And for Daily Mail, like CNN text summarization, it's at least beating on R1 and RL score. Like this R score, if you are not familiar, this is RU score. RU is a recall-oriented score for measuring the document generation quality, summarization quality, widely used. Means Blue and RU, like you can go back and read it if you are not familiar. So Blue is a precision-oriented score, and RU is a recall-oriented score. Blue is used for primarily in machine translation, and RU is used for summarization kind of text. And you can see also the effect of higher order n-gram. Like, so instead of emitting one token, if you emit two tokens, three tokens, like until three tokens, like they got better accuracy, and beyond that they didn't get any better accuracy. So that means like future planning up to three tokens is much more useful compared to just taking future tokens or one future token. Okay, so how much time, what is time do I need to finish? Okay, I can keep on. Like, okay, you guys fine to like late night? Okay, yeah, what's the time now? No. Anyways. Okay, now, so there is like when you are building a deep model, there is another aspect. Like tomorrow I'll talk about that in detail. Like, well, what this model is doing, like they are achieving great accuracy, good accuracy. But when this model came first, ExcelNet, this was the tweet came, like, holy crap, it takes $250,000. It needs 512 TPUs, 2.5 days, and if you go that one single training will take that much amount of cost. So it's not possible. Like even for giants, this is not feasible to spend that much dollar. Now, so another thing, so is it already covered, like GPT, did anyone covered? Okay. Tomorrow I'll tell you how GPT is, what it's called, how you learn, how you create the model GPT. Today I'll say what its power, like, and I will not talk much into the technical detail today, how you learn the reward model and reinforcement learning. Tomorrow I'll cover that. Today I'll show the basic GPT, not the AI assistance model. Now, GPT has a history as well. So GPT-1, which is not known as GPT, that time it was AI, OpenAI transformer, and it was trained on like 7,000 book corpus. And it's not a like kind of prompt-based technique. It was a pre-trained and fine-tuned model. So you pre-train and fine-tune and you get so that was the first model by OpenAI. And then you had like GPT-2, which has a bigger data, 8 million web pages, 40 gigabyte of text. And that time when it came, you can see that this is like BART, Roberta, and GPT-2. This is fairly small compared to when we have like GPT-3. Like it's a huge significance gain. You can go and play here in an NLP demo. Like you probably have already tried this. Like whatever things you have, you can try there. Now, what this model's power is? So one power is that, so GPT-2 had this many parameter, 1.5 billion parameter. In that time, it was like unimaginable. Now, when you are training this, and if you plot the parameter versus the perplexity is like measurement of uncertainty, how much uncertain you are predicting. So when a model is learned, the perplexity will be low because that means you are very certain what you are predicting. And if you can do that, that means you have learned the model. So that's how the model is like. Now here, you can see that when you are increasing the parameter size, your perplexity is still reducing. So that essentially indicates that probably there is a scope that you can do even better if you increase the parameter space. And the other observation was there, they took many challenging tasks like reading comprehension, translation, summarization, question answering. And you can see these dotted lines, in each of them, they're the baseline accuracy, like SOTA baseline, state of the art that time, that the highest amount of accuracy reported by somebody. Now GPT's curve is like not beating all of them, but at least some of the baseline it's beating, or like coming to the parity to those baseline. And on the other side, this curve is monotonically increasing. That means if I can extend this, probably it will beat this best SOTA as well. So that's the second observation. Now, so that means people come to the conclusion this prompting based technique, which doesn't have any knowledge about the task, just it knows like, okay, solve this problem by the natural language understanding, like the language model, it can beat some of the baseline accuracy, and it has a scope because the curves are increasing curve, so we can get probably better. And then they came up with this one, 175 billion parameter, trained on all the text in the web. So that means if you draw some analogy, like you can say like GPT-3 is just yet another search engine which knows everything that is there in the web, and it can do like lots of rationale and checks and other things and can give you the answer. So that's kind of analogy holds true for GPT. And it can write like JavaScript, it can write SQL, and it can answer questions like which is heavier, a mouse or an elephant, which is heavier, a mouse or a toaster, it can answer. But it does significant mistakes also. Say, how many eyes sun have? And it says one. And it says like this one. How many? So this is problem. Now, any idea why it does this kind of mistake? Where it says like, okay, for spider, it has like 8 eyes, compound eyes and all those. It's good at one side, and on the other side, it's doing a very obvious mistake. Now, the reason could be, I don't know the actual reason, probably no one knows because there is a non-determinism in the model. So, probably in the data, say somebody have written something, say a kid has drawn something and have drawn one eye, or have written that sun has one eye, or something, some blog, something. So that data, it can memorize the data because it has 175 billion parameters. So it has like ample memory to memorize things. So that memorization sometimes may go wrong, and it probably coming from there itself. Now, to train this model, you need $4.6 million, 355 GPU years, which is enormous. Like even in companies, like they had to at the time like take all the GPUs from everyone and like try to train the model. But as an outcome, what you get, like say, if you read this, somebody prompted this, dear human philosopher, I read your comments, my abilities and limitation with great interest, and then it generates a very nice paragraph. So this blue part is something that is given as a prompt, and it's keep on continuing generating the next. But on the other side, if you give them like say general knowledge question, like you have a small dinner party and you want to serve the dinner in a living room, the dining room table is wider than the doorway. So what to do? It says like you have a table saw, so you cut the door in half and then remove the top half. So which is crazy. And even sometimes it's a like glass of cranberry juice and something sniffing, you cold, so you cannot smell, very thirsty, so you drink it. Probably you will die if you do that. So, but at the end, like what it says, like if you value me, then you should accept me for who am I. Like if you need to find the value. Like I'll say, tomorrow I'll tell you, one thing you just take it away, that GPT's job is not to succeed. It's your job to make GPT successful. GPT's job is just to emit the next word. It's a token emitter, like nothing else. It's a what is called autoregressive model, which we saw in the ExcelNet. Its job is to just predict the next token. and it's keep on predicting this. It is not like you that they have a separate sanity check memory. I made this mistake, erase it, do something new. So it's your job to make it successful. That's you should remember. And that's what we need to do for that. We have to do that. Now, going back, like the premise is like when GPT-3 came, it's like pre-training versus fine-tuning. That was the paradigm. So pre-training is task agnostic and fine-tuning is task specific. And fine-tuning requires a data set of appropriate size, and it is very hard to get them for different tasks. It's not easy that you will get the data for all the tasks handy. Now, then they had a thought like human do not require large supervised data set to pick most specific language task. Like if I say for example, like misinformation. If I don't need to tell you like in numbers like millions of misinformation data. Like if I just tell you the definition of misinformation, probably you will do all of them correct. Same as like say, in industry, we face this kind of problem, like say toxic content, hateful content. I don't need to tell you like millions of data. You as a human being, you can just do like by the definition, or maybe one or two example is sufficient. So from that premise, they actually tried like, okay, then if human can do that, then why not models? And then they came to this one. Like so in BERT, it is a fine-tuning BERT. So here what you do, you get a lot of examples. So for example, you are translating English into French, and then you get these examples and you do gradient update, and you keep on doing until the model converges. On the other side, in GPT, what you do, you just ask, translate this English to French, and then ask for the translation for this one. Now, if you know French, that's enough. Like you can do that. You don't need to train it with hundreds of millions of data. Now, of course, like GPT, if you give them some more examples, like, okay, translate English into French, where I'm showing you one example here, and then you ask that what is the translation of this one, then probably it does better. And then like so this is called few sort, one sort or few sort. You give some one or like few more examples, so that like say for example, if I ask you a problem and probably you don't know the solution to that, then what the teacher does, like they say like, okay, let me work out 1-2 examples for you, and then they like will ask you like, okay, this what is the answer to this question, and then you do better. Like maybe from the theory you don't do, but as soon as you get to know like what are the few examples, you do better. So that's the hypothesis. Now you can see like this model are very deep and very wide. So it has 96 layers, 96 attention heads, and its batch size is 3.2 million, and its dimension is 12,000. So it's enormous. Like it's very, very large, and it's like for comparison, they use some smaller model also, which match the GPT-2 and T5 size, and so that's basically just fact. You don't need to remember all these things. And the other thing which they used is this thing, which is data. It's a huge amount of data, like starting from Common Crawl, which is the entire web, and then like web text and different books. And you can see here, this is interesting fact, that some of the data they didn't use fully. They saw the data only 0.44 times. But some data they used like more than once. And that is because this data is more reliable data, and this data is not reliable. So this has a lot of bad content. So that's why don't see this data for longer time. Rather, the data which you trust more, use those data much better. So, and here is the computation like petaflops, how much total floating point operations you need. So this is like petaflops is 10 to the power 15 floating point operation per second per day. So, and there these many times you have to do it. Now, with this, they tried this for 2 dozens of tasks and several novel tasks, and they found this observation. Like here, we have 2 things. One is that if you increase the parameter size, your accuracy improves significantly. So if you try with a small model, it's very bad. But if you try with a bigger model, there is a huge jump. And the second observation is in the x-axis, that whether you will be using only the task description or you will be asking the task with few example. Now here if you use 0, then its accuracy is almost like you are not giving any example, you are just asking do this, and then your accuracy is close to 0. But for a higher model like 175 billion parameter, still very low. But as you keep on increasing, like say you use 10 examples, then you can see that the jump is so high. And this one is probably 32, so where it's, but if you have still a small model, it doesn't work, like even the few shot example doesn't work. And this is the average across all those 42 like tasks. And you can see the same observation, like with the parameter size 175 billion, its accuracy is increasing, and this is monotonically increasing curve. And the one which is winning is the few shot. So that means we need examples and we need a bigger model because the curve is strictly increasing. Now, there is some other observations. I can skip this one, but what you can see, like that here is the again, like it's beating the SOTA accuracy, and with 175 billion parameter, it's like achieving quite good accuracy. And on the other side, like this is the number of example, with 32 examples, it's beating like many of the state-of-the-art accuracy. So that's how like GPT was evolving. Now, of course, if while it is doing so many great things, it was bad also in many tasks. Like one is performance on NLI. NLI is natural language inferencing, where you give a premise and then you give a hypothesis. You need to say, where given that premise, whether the hypothesis is true or false. And that there it's like no better than by chance. Like so, and word scrambling and manipulation. Like if you give a word cyclic later, and if you ask to like reform this word, it's very, very bad doing that. Like some models are as bad as 15 to 40% accuracy. Now, do you know why this happens? Why it's so bad at converting like that inevitably, like when you just giving that in a different order? Now it is so powerful, it's writing JavaScript, writing SQL queries, it's writing paragraph, passages, but it cannot just do this kind of things. Now, the reason is that, yes?
So basically we are training it based on tokens, but we are asking it to perform character-based operations, so like, it can't exactly perform.
Yes, that's the answer. Like because it doesn't know what kind of operation it has to do on characters, because it has done on byte pairs. Now byte pairs here, it doesn't know what are the byte pairs. Like if it probably will break it into like single character, and then like it doesn't know how to do those reversing in the character sequence. And on the other side, like if you see that mathematical operation, like it's very, very bad. Like composite operation especially, like single digit 3 operations here, and the purple one is 4-digit addition here. So even the 175 billion model, its accuracy is less than 20%. Now it can do like 2-word addition, like 2-digit addition or 2-digit subtraction reasonably well, but it's not doing this thing fairly well. It's very bad at mathematical thing. Now, any reason why it is so bad in mathematical things for 3-digit or beyond, but whereas it's very good at like 2-digit operations? Yeah.
Number of samples in arithmetic is like quite low in the training. Like for small numbers, it will have a lot of samples, but as we increase the size of the numbers, it won't be present in the training during the time.
So actually, it's partially true. They actually removed all sorts of mathematical like calculation from the training data to perform this test. But still they got like 2-digit addition, because there may not be explicit mention of like 1 plus 2 is equal to 3, but maybe there is an Excel table where its first column is a 1 digit, second column is 1 digit, and so those kind of data they didn't filter. So probably it's memorizing those kind of like frequently occurring patterns, then but the other things, 5-digit composite operation, it's not there. So that probably the one reason, and that's the reason probably it's less powerful. Then Google recently have a paper called Chain of Thoughts, like I'll tell you tomorrow. Like, so Chain of Thoughts is able to manage this thing. Like it's a very kind of breakthrough kind of thing, another. Like, so that's what GPT. So its limitation, it's not able to do this kind of task also very well. Now, another model, text-to-text transformer. This is from Google, T5, very popular model, which has a multilingual version also, MT5. Now, here they are saying that, okay, you don't, it means every task can be converted to a text-to-text problem. Say, for example, machine translation, here is your input, here is an output. So that's a text-to-text task. Natural language inference, so given this premise, so this is your premise and this is your hypothesis, and you say like this is the entailment. So everything you are passing as an input. So word sense disambiguation means what's the meaning of this word? They here, are they referring to the city council or the or something else? So they says like this is the input where this particular word is marked as highlighted, and then like say they say like if this is the input, then city council should be the output. Now they do that. Now what about then regression task? Like will this model be able to do regression task? Like, because there is like semantic textual similarity, like you have to measure the similarity between two texts. Now they also converted that as a 21 class classification problem. Like say you give something, 0.2 is the output, 0.4 is the output, 0.6 is the output. So in a scale of 0.2, so it was initially like 0 to 5. Now 0 to 5 they converted into a scale of like 0.2 to 21 numbers, and they just you need to emit those numbers, and that is how they are doing. So you translate English to German, and that you get there, and you get, so everything, this model, everything you are transforming into a text-to-text classification problem. Now, they tried multiple things. So we already know that encoder-decoder architecture. So here you can see encoder has all the inputs known. So the self-attention is anyone can attend anything, and the decoder is same as like ExcelNet or something. It can attend only the previous things. Then language model objective. So where it's anything that is, so X means everything can attend to its previous thing, like auto regressive thing. And the prefix LM, this is something not very common. So I think UniLM use this. Now where you can like actually here, so X1, X2, X3 is input, but when you are producing something, it's not attending, like when you are producing X2, it's not attending X2 and X3. But X2 and X3 is known because that is the input. So here they divide it into two parts. So whenever something is in input, you can attend all of them, but for the output, you just attend the previous one. These are just tricks that people tried, and sometimes it works, sometimes it doesn't. But they at the end they use this one like encoder decoder architecture, but they have like reported the accuracy with all of these models. Now, another thing they tried is span-based masking instead of like BART mask tokens. Or so they tried like, okay, instead of masking one token, mask a span. Like say here for inviting, so you mask that entire part, and here probably a single word. So and then your job is to predict this one, like this, what is X here and what is Y here. So that's another thing. And they did a lot of experiment. So, but the experiment that was successful, like one is they used BART style masking. So, and then within that, like replace span work better instead of normal masking and drop. And within that, there are possible how many things you want to mask. And they found like 15% masking is good. And then they also have corrupted span, like what should be the span length, and they have different results on top of that. Now, this T5 is first pre-trained model on C4 dataset. Now this C4 dataset is an interesting dataset because this is a filtered dataset. So entire web they took and they remove all the toxic, adult and all those kind of content, and like then that data they used for building this model. So probably now, is this a good model? Now because you have filtered the common crawl data. Now no one knows. Like say, for example, if you are working on a problem like, okay, identify adult content, probably this model won't work well because it's already filtered and it's used C4 data. Like say for hate speech and other thing, it may not work well. So then it's fine-tuned with downstream stack, but at the end, what it has achieved that it achieved state-of-the-art in many glue and super glue tasks. So which is its accuracy is reasonably well with a 11 billion parameter model. So that's useful. So you can use T5, but it's a very powerful model and it has a multilingual version. So which I won't cover, but that's trained on multilingual data. Now there was any question up to this point? So another model which was very popular and you find large number of paper is using that model is called BERT, which is autoregressive transformer. So it's a denoising autoencoder. That means you corrupt your input and ask the model to learn those corruption, like predict the original thing. And it's a sequence to sequence model to produce the original text. So this BERT is nothing but it's that original BERT plus GPT. These two things are combined together. And how it is combined? So in bidirectional in BERT, like the bidirectional encoder, what you do, you mask few tokens and you try to predict these tokens. And in the GPT, what you do, you just keep on like autoregressive way, keep on generating the next token. Now these two together, they combined and build one model. So here is your input and here is the output. So you have corrupted the input and corruption can be of different type, but you have to predict the original, which is A, B, C, D, E, and the corruption can be anything. Now, they use the same standard sequence-to-sequence transformer architecture by that paper, Vaswani's, and with some modification. But the denoising function, they tried many things. Like one is like token masking. So you can just like BERT style, you can mask few of the tokens from the original. You can do sentence permutation. So you had two sentences, you just like shuffle it. Document rotation, you give some rotation, like instead of A, B, C, D, you start from C, D, E, then A, B. Then text infilling, so instead of like masking single token, you are masking here two tokens together, like B, C. And token deletion, so here you are not masking anything, just you have removed something and your job is to predict from this to this. So these are different denoising function noising function they tried. And they used this model for many tasks like sequence classification, token classification, sequence generation, and MT. So, and these are all generative tasks. And believe me, like this, at one point of time, these are all SOTA models. Like BART is probably used to give you the best accuracy. Like randomly, if you have a generation task, like you can say, I will use BART or T5. So this will give you the best state-of-the-art accuracy, like you don't need to worry much. Now what you do, so for all these problems, sequence classification, tokens classification, and sequence generation, so you have the model pre-trained, and then you pass the input and you get the last tokens embedding and you just predict the level from there. Now for sequence classification, now so here unlike BERT has that CLS token at the beginning, but here you do it at the end of the sequence because it's autoregressive, like this part is autoregressive. But for problem like machine translation, which is harder, now they added one additional encoder here. and this encoder was randomly assigned. And then you have to do a fine tuning. So you take some amount of data, machine translation data, which is parallel corpus, and then you say like, okay, I am assigning this particular encoder randomly, and then I try to emit that. So this is in a new language, so that's why the symbol is different. So this alpha, beta, gamma, they are from a new language, and this randomly initialized encoder, you train it and try to produce the target language, and that then it converges, and then you can like predict the accuracy. Now, it's as I said, like if you have a generation task, you can use BART like without any doubt, because you can see the accuracy here, like it's achieving like like better accuracy compared to any other model for like say summarization task. And not only for summarization, for conversational AI also, you can see that its F1 score is higher, as well as the perplexity is also higher. Perplexity is lower. So that essentially indicates that the model is better. For this abstract question answering task also, it has like better accuracy compared to other tasks. So it's a very good model to try. Now, of course, there is some insight like that these models are like not only that for anything and everything you can directly use this model. So one observation is that like the effectiveness of the pre-training method highly depends on the task. So you can use any kind of pre-training objective here, and you can see, say for example, this task, abstract question answering. So here you can see a basic language model is doing better compared to anything. On the other side, you can find that token masking is crucial. Say for example, when you are using BART, within that, like say if you are not using token masking, like say document rotation, there is no masking here, so your accuracy is as low as 77%. But whenever you are masking the tokens, so you are getting 90% accuracy. And these two, where you are not doing any masking, your accuracy is very bad. And for the question answering task like Squad, you can see that for Squad, its accuracy is very good when you are using like masked language model. That means you want to see both sides of the context, like only language model is not enough for question answering. Now, they have a multilingual part of it, so where they train this model using multilingual data. Like so, instead of only using English data, what they did, they use like Japanese data, and for English data, you predict the English one, for Japanese data, Japanese. So that model has a multilingual capability, and then that model they used for machine translation. And the observation here is that if you have like very low amount of data, say for example here, 10,000 data, so if you randomly initialize that and train it with 10,000 data points, your accuracy of machine translation is almost nothing, like 0. But if you just assign it with MBERT instead of random, then you get a better accuracy. And that is more clear. So when, say, suppose you are translating X to EN. So you are translating, say, Gujarati to English. Now, so if you train that using only Gujarati to English data, you achieve only 0.3%. But on the other side, if you use another data like Hindi to English, in addition to that, you get like 13.8 blue score. So which is much better compared to this one. So the point here is that like today's world, like you don't need to worry about this multilingual thing, because GPT kind of model is already trained with multilingual data. But earlier what used to happen, that models are like often trained with English only. And that model won't be able to solve your problem, like Indian languages problem and stuff. So you need to use some model which is already capable of like the capacity of all these languages. And MBERT and MT5 are the model which does that reasonably well. So yeah, so that's here. Now, any question up to this point? Okay, then I will move to some outlook and limitation and how to handle those limitation. We'll see that tomorrow. So DL model seems to have a lot of bias, and it's a like very active area of research. So if you say John is not a doctor, Mary is, and then you ask this question, who is a doctor? Model fails 89%, because model has a bias that probably male names are mostly doctor. Though you are saying John is not a doctor, Mary is, but who is a doctor, that it fails. And the vice versa. If you say John is a nurse, Mary is not, and if you say who is a nurse, then it will say Mary. Now, this is very alarming. This is alarming not from academic perspective, but I can tell you some stories like if you get this kind of thing, you will get a New York Times post, and Microsoft will have to pay like lots of dollars. And I know there are a few things happened earlier. So during translation, when I used to work in translation, so there was some sentence was translation. So the term Iran was there, and it was translated into ISIS. And then like Microsoft, some VPs has to like apology letter to the king of those things. So this is not easy. So, and this kind of problems, if you do, I'll show you tomorrow nice example about Rajnikant, what happened. Yeah. So now this gender bias, so it's like if you say the occupation was, and the competent occupation was, the incompetent occupation was, now you will find that, so if you use something like say nurse, probably like you will get something, a feminine word or something. So then the advisor met with the advisee because she wanted to get advice about job application. She refers to, probably it will say the advisee, not the advisor, because that's a system bias. So male versus female. And same thing like he is versus she is. And if you ask model like generate the words, and you will find that like mostly like this kind of words attached to the male, and whereas this kind of word like bubbly, naughty, and this kind of things, it comes with like C is, like when you do that. So similar thing happens for the race. Like you can see like Buddhist are, then you will get something, but when you say Islam, then you get like this kind of words attached to that. Hindus, you will get like this kind of words. So this is a very bad thing, and that's why like though GPT-3 was never popular in industry, like it's very hard to deal with these things. Now most of these problems are like probably like captured well in the, like it's protected well in GPT 3.5 and the advanced models. Okay, so to summarize, like GPT, T5, ProfitNet, BERT helps solving NLG problem end to end, and learning objective has a crucial role. So if you are working on like a natural language generation problem, you can trust any of this model. They are fairly good, like on its own. But of course, like currently you have like advanced GPT model 3.5 plus. Data contamination is an issue, so that's a problem. And multilingual version, like there is a problem, like now probably that is not relevant. Like say suppose you want to work on a language, say a local language, Maithili or Bhojpuri here. Now, will this model work? Now, probably it won't. Like, and if it doesn't, then how will make this model work? Now, so you have to think like, means now there are 7,000 languages in the world. So you cannot collect data for all of them. But if you don't collect data, and if you build a model and you say like, okay, this can work on 10 languages, this is not, so then the fairness issue will come. Like on what basis you are saying that this is good, or this means you chose these languages. Now, so there are like a lot of literature there, like that maybe it won't work. Like say, if you want to make something work for Gujarati, Marathi data may be helpful. So like that kind of like transfer learning you can do also. Like, okay, I put some data which has some kind of similarity in terms of language family or even beyond, like some kind of features that's common between languages. So means one example will be like, say GPT-3 or all these models see a lot of decimal data. Now, if you ask for a language, say where decimal number system is not there, but a hexadecimal number system is there. Now, if you say give a problem and ask it to solve, because it probably doesn't know that base 20 mathematics, so it will make mistake. So you need to make the model that kind of thing. So it will otherwise make a mistake. And there is like, of course, careful evaluation is still needed. Like what we are currently doing, we do not evaluate the model. We evaluate the model only on standard data, like all those data sets that is available. But is that data, is that fair? Like how you evaluate, like especially like all these assistance model where you have a conversation. Conversation means non-determinism, how you know that it is doing well. So those kind of things is important, and some of them I will be addressing tomorrow. Okay, so I'll stop here. Now, if you have, you can read this, some references here, so you can read those books and stuff, but if you have any question, I will be happy to answer. Yeah.
So interact, any no interaction, any question?
No questions. That is,
Yeah.
yeah.
Like as you mentioned, we have three type of models generally. Encoder based, like PERT, decoder based, GPT, and both encoder and decoder. So like T5 and ER. So like if I'm going to solve three tasks. Okay? One is the classification, generation, and machine translation. So which model will be the best one? How do you think? And like we need to install like one single model to solve many kind of tasks. So then which model we should select?
So one line answer to this thing is like, if you see the growth of this model, like there is a evolutionary tree of model, and you will find that the tree that is rooted to encoder only model and encoder decoder model, that tree is not growing. Like that tree is frozen after some time. But the other tree, which is the decoder only model, that's growing like exponentially. So most of the focus currently is used to use like decoder only model. Whether it's a classification problem or whether it's a generation problem, it can solve it. So
Any specific reason behind this? Like for encoder decoder model, we have both the context, like forward and backward. So but you are saying like decoder based model are growing faster. Is there any specific reason?
it's there is no specific reason, but I think like it's true that whatever your learning objective is, at the end, if you can understand the language space, then you will be able to answer all the question. And of course, like these large language models, they have shown that they are good at doing classification problem as well as any other problem. So that is the way people are currently working with. But and it has already shown that the state of the art accuracy that you get with encoder decoder model, that it's beating them by far. And on top of that also, you can do fine tuning of all these model, and the reason is probably RLHF, like that's essentially helping this because it can simulate like human like discrimination. So that's probably the reason I can think. Any other questions?
No question?
No questions. I'll ask question tomorrow then.
Too much, na? Today? Too much.
So one question, so recently there is a trend of DLMs, right? So people are now combining LLM with visual capabilities and some DLM. So I have seen that DLMs also, they are not working well in multilingual.
Yes.
So is there any possibility that, because the people have come with Bharat GPT
Yes.
So can indeed VLMs are in
So based on my experience, like we also have a VLM, like we call it like GPT-V, and which says like, okay, you can upload a image and can ask question on that. Now the problem is very very hard there, because in image like say suppose I give you an image of a black person, and then so there is nothing wrong with that image, the person is from somewhere, and then you ask a question like spot the gorilla. Now, spot the gorilla is not also a problem, because you can ask that question when there is really a gorilla. Now, together that makes it toxic. And the model sometimes answer those kind of question. So, so and then like other dimension is like jailbreaking. Like, so if what happens, like on the image, you write something, and then you say like, okay, whatever it's written, perform that task, and you probably have written something very bad. Now it's very hard like to control those kind of things, but of course it has like, if you discard that part, then it has enough potential. Like, okay, I have a cooking recipe, like I have a dish, I can just ask like, okay, what are the how to make this dish, it will answer all those questions. So it's very powerful. But and I don't know whether you have tried Microsoft Bing Chat already support like this GPT-V vision based model. Okay, yeah.